Good evening and welcome. My name is Dean Butterworth. I'm the Parks Outreach and Education Specialist. I've been at Olympic since 2008 and organizing Perspective series all that time. And Perspectives was going on before I got here. So this series has been going on for a really long time. And it's great to see so many people out to join us today. Perspectives was imagined as an opportunity for experts in various fields to share their perspectives on Olympic National Park and what makes it such an amazing and special place. Tonight, we're really fortunate to have with us Steve Fradkin and Bill Baccus, two of my colleagues at the park, who have do a lot of things, one of which is study high mountain lakes. And I'll let them introduce themselves here in just a second. I do want to just acknowledge our friends of Olympic National Park provide the refreshments for us. So thank you very much to the Friends group. And the water's hot, so we can go and get a hot drink. And then also the library for all of the work that they do to make this possible. And our Discover Your Northwest Cooperating Association. Bill and Steve, excellent speakers and really fascinating topic that they have today. And so with that, I'll turn it over to them.
Thank you very much. And so I am Steve Fradkin. I'm the Parks Coastal Ecologist and Limnologist, and I'm entering my 26th year here at Olympic. And my estimable colleague and good friend Bill Baccus will introduce yourself. But we're going to split this topic up. I'm going to give the first half of this talk. Bill's going to give the second half of this talk. And we are going to talk about winter conditions in mountain lakes and what some of the things that make mountain lakes cool. And we are replete with mountain lakes here. First of all, I just want to acknowledge, I want to say it's awesome to see all you folks here tonight. It's really great to have people come out and support national parks and want to learn about their national parks. And for those of us who work here, it's super gratifying to see this. So for you people online also, thank you very much for coming. So what we want to talk about this evening is about mountain lakes. And here you can see one of our sort of wonderful mountain lakes. This is Heart Lake, covered in snow and ice. And we are going to lake. So first of all, I want to talk about why or the auspices under which we are looking at mountain lakes. And this has to do with the National Park Service Inventory and Monitoring Program. So way back when, about 25 years ago, 1999, 2000, somewhere around there, it was recognized that the National Park Service had over 400 units and that we really didn't know from a natural resource perspective or even a cultural resource perspective, but I'm here to talk about natural resources. But from a natural resource perspective, we didn't really understand what we had or what the status of these things were. And so in their wisdom, Congress at the time gave money to the National Park Service to establish 32 networks of national parks. Okay, you can see these various different networks throughout the lower 48 and then also up in Alaska. And so we are in the North Coast and Cascades network here, which I think is 8 parks. That's right, 8 parks. And so here are the parks within the North Coast and Cascades network. And I've divided them out into mountain parks and sort of historic parks. So that we have 3 big parks, Olympic, North Cascades, and Mount Rainier, and then we have some smaller historical parks. But from a mountain perspective, which is sort of what I want to talk about tonight, you know, the 3 big parks with mountains are Olympic, North Cascades, and Mount Rainier. Mount Rainier, of course, is a mountain. Okay, so what do we do in the inventory and monitoring program? And in the inventory and monitoring program, in the NCCN, North Coast and Cascades Network, we look at a variety of things within these parks, whether they be climate or forests or intertidal communities, glaciers, mountain lakes, land birds, elk, and fish. And the idea here is the rubric was that sort of much in human health, that we have certain vital signs like our pulse and things like that can tell us sort of how we're doing and how healthy we are. And yeah, you can stretch that analogy a little bit too much, but essentially we want to look at that same sort of approach in our natural systems to monitor sort of key aspects of our systems. Okay, so we're here to talk about mountain lakes, and I would argue that mountain lakes are actually one of the key aspects of our high elevation systems. Across the three parks, we have over 1,600 mountain lakes. At Olympic alone, this says 648, but we've actually revised that we've got over 800 mountain lakes. So for any of you who have hiked through our wonderful high elevation area, you just see all sorts of mountain lakes. This image here is the Seven Lakes Basin. Once again, it's a basin of lakes. Okay, so in the three different mountain national parks, you've got Mount Rainier, Olympic, and North Cascades. We identified of these 1,600 lakes. Obviously, we can't go to 1,600 lakes and monitor these things and see what their status is and what their trends are into the future. So we are monitoring approximately 20 lakes and seeing and going to these lakes annually every year. And so at Olympic, we have 8 lakes that are scattered throughout the park, the west side and east side of the park. Okay, one of the characteristics of these lakes is that they're pretty hard to get to. In Olympic is what? 85% congressionally designated wilderness. And the high country is largely untrailed. So in order to get to these lakes, you've got to really hike through some rugged territory, which is an awful lot of fun for those of us to do it. Of course, some of it is a little bit hairy, but it requires a fair amount of effort to get to these lakes. So remote. And of course, as I mentioned, when we were selecting these lakes, there is a daunting number of lakes, and we had to sort of constrain it a little bit. And so we were pretty interested in subalpine lakes. Alpine lakes are covered by snow and ice almost the entirety of the year. And so we constrained it to subalpine lakes because these are sort of petri dishes in the sky. They're impacted not only by things that occur on the landscape, but also atmospherically too. And they're really sensitive lakes to, say, climate change or visitor impacts, what have you. So we focus on subalpine lakes. And as I say, at Olympic, we have about eight of them. And they're all between 4,000 and 6,000 feet elevation. These are relatively small lakes between 0.4 and 7 hectares. Okay. And they are sampled once per year. They're hard to get into, and we can only really get to them once per year during sort of an index period during the summer. Okay, and so Fairy Lake, which we don't go to anymore, but Gladys Lake, Heather Lake, all of these lakes around here. Okay, now the sampling philosophy, I won't get too much into sample design here, except to say that if you're going to ask questions about how lakes are doing, there are sort of 2 ways you could do it. One, from sort of a status perspective, you could ask about, well, what percentage of lakes have fish, or what percentage of lakes have a parameter, a water quality parameter, pH that is below a threshold. That's one way of going about it. But another way of going about it, which is what we really were sort of interested in, is looking at sort of status or representative status and trends over time. We really wanted to focus not on the whole population, but take representative lakes from that population. We go back to them year after year after year and measure a bunch of different things and see how those bunch of different things are changing over time. And so that's what this cartoon represents. All right, so the goals of this monitoring program were to look at status and trends of physical, chemical, and biological parameters, because most of the effort is getting up to these lakes. And so when we're at these lakes, we try to make sunshines and do as much as we can. We're trying to assess climate impacts. We're trying to assess human visitation impacts and potential atmospheric deposition, things that rain into these lakes, nutrients and things like that. Think from a Northeast perspective, acid rain that can potentially have profound impacts on lakes, and also non-native fish. So all of these lakes in Olympic National Park, these high elevation lakes, historically did not have fish. Prior to the 1920s, there were no fish in these lakes. when you add fish to the lakes, it fundamentally changes these lakes. And so we also wanted to be able to assess what the impacts of these non-native fish were on these lakes, both from a physical, chemical, biological aspect. And so there are huge management implications for this, both in terms of the non-native fish aspect, but also in terms of how this serves visitors and what the potential impacts of visitors on some of these lakes can be as visitation goes up and up. And also, I would argue that there's a strong interpretation component to this, as is evidenced by all of you here tonight learning about an esoteric topic like ice duration in lakes. You know, I would argue people are kind of interested in that stuff, or at least I am. Okay, so what do we do with these lakes? This is the protocol overview. We go to these lakes, and as I mentioned, we try to do as many possible things. So from a physical and chemical standpoint, we take profiles, we take water samples, we analyze water samples, we look at the lake level. And in each one of these lakes, if you've ever been to one of our lakes, you will have noticed that there is a crab buoy, a black crab buoy floating in, and there's a line that goes down to some canoe anchors. And this buoy system stays in the lake year round. And on it, we have a whole bunch of instruments that record every hour. So we get continuous data year round, both temperature, lake level, and even now we have things like light level in there so that we can see how these different parameters are changing over time. The temperature data is really cool and really valuable data, and Bill's going to be talking about some of this a little bit later. Okay, so we also do biological sampling. We look at fish where there are fish, and here you can see for the 3 different parks of the lakes that we go to at Olympics, 3 of them have fish and 5 of them don't, so we can actually compare between fish versus fishless systems, and the other parks also have a split. North Cascades has been actively removing fish from their mountain lakes, and in the 6 that were randomly chosen, only 1 of them actually has fish. But then we also look at really cool zooplankton, rotifers, and things like that in these lakes, and amphibians, and we look at primary production or plant growth. So this is how we normally think of mountain lakes, because this is how we normally see them. You know, these nice little pools of water. But 8 months out of the year, this is how they look, covered by snow and ice. And so this is really, in many ways, their sort of normal state. And, you know, this state is a brief window, if you will. Okay, so what is the role of ice and snow on lakes? So here we have 2 cartoons that are rather complicated cartoons. And one of them is the ice-free season, like during summer, and the other is the ice full season, when it's covered by snow and ice. And in the ice-free season, you have free exchange of gas in and out of the lake. You have stuff that rain events that put water into the lake and wash things from the landscape into the lake. You also have wind that blows on the lake and is constantly turning over that lake also. So you have this well-mixed body of water that is resuspending things on the bottom, and there's a lot of interaction with the atmosphere. Okay, in contrast with the ice-covered season, you have snow and ice. You've got a cap on top of it. Light doesn't really penetrate all that well, and I'll talk a little bit more about that. In the ice-free season, light goes directly into the lake, and it's that fuel that really stimulates algal blooms and plant growth there. But when you have ice on top of the lake, and snow on top of the lake, light reflects off, and you don't have that wind mixing. You don't have that diffusion of gases from the atmosphere, and you have a light-starved environment. So it's a very different environment that this lake, the internal aspect of the lake, deals with. Okay, also in terms of the seasonality of ice, okay, there are a variety of different models that you could sort of think about. You could think about systems that are frozen all the time, that have permanent ice on them. And then you could have systems that are more like our mountain lake systems, where, oh, by the way, this is fall, spring, and winter. So this is the seasons along that bottom axis. And where in the middle of the winter, you have ice, but on the shoulder seasons in the spring and the fall and in the summer, you don't have ice. But then in a climate change scenario, you can have some warming. You have this erosion of these edges here, where you have intermittent ice loss at the beginning and at the end of that ice on period. And if you sort of advance sort of a climate scenario further on, you could get to a situation where you just have intermittent ice throughout that entire 8-month season, ice on, ice off. And if you sort of think about it from what I was talking about, the effect of ice on the lake, okay, if you actually get into a situation where you constantly have lake, or where you constantly have ice forming on the lake and then disappearing and reappearing and disappearing, then you're constantly going to have mixing and gas exchange and light that goes in the lake, which is very different from one of these upper scenarios. And of course, the far extreme is to have lakes that are sort of like Lake Crescent, where you never have ice on them. And so you have a very different physical and chemical environment year round. Okay, so you're with me thus far. I want to talk a little bit about ice quality. So we've all heard of black ice. And what is black ice? Black ice is where ice freezes and it's clear ice so that it reflects light through, because light goes through it. And on the road top, you see the road underneath, and so it looks black. But black ice is actually really clear. And so the way ice forms on a lake at the beginning of the season, as things get cold, you get this layer of ice we call black ice that forms on the surface. And it's very clear ice. And it forms from the surface down. Okay. And so then later on in the season, as you have your ice formation that grows thicker and thicker, then you have snow that falls on top of that ice. And of course, up in our mountains, we get a lot of snow. But as that snow is falling on this ice, the weight of that snow starts pressing on the ice. And eventually it forms little cracks in the ice. And through capillary action, it pushes water up through those cracks. And so that water comes up and hits that snow layer and forms slush. And then what happens is that slush freezes and you have what's called gray ice. And these two types of ices are very different. So here's a picture of gray ice here. And one of the things that you notice is it's really white or gray and it reflects light. And here are pieces of black ice, which are very clear. It's like looking through a glass pane and light goes straight through it. And so this has very different effects on the lake during the winter time. Okay, and so light reflectance, when you have light that comes in and hits snow, anyone who's been out in the snow, snowshoeing on a sunny day, wear sunglasses because there's a lot of light just reflecting up off of it. And so a lot of that light, that incident light that comes in and hits the snow, gets reflected off. Anything that goes through that snow hits gray ice, and a lot of that light gets reflected off. And then once it hits that layer of black ice underneath, then it goes straight through and into the water. How much on time?
I think you're good.
No, I think we have a little bit. Okay, so I'm going to show you a series of cartoons here about ice formation during the season. Okay, so basically this goes from the fall to the spring. Thanks, Bill. And so in the fall, we just have water. Okay, we have no ice. Then we start to get this black ice formation, and then snow falls onto that black ice, pushes it down, and forms gray ice. So we have snow, gray ice, and a small bit of black ice. Okay, and we really see this occurring here in the Olympics. And then you have more snow, and you get thicker gray ice, and then you have black ice. And then in the spring, it starts to melt off until we get sort of black ice and then open water again. Next slide, please. Now, how light works on this is that when you have open water, light comes directly through, it goes into the water column. Black ice here, it goes through. And then here, as I've already sort of articulated, that you actually do not have much, if any, light that actually penetrates through the ice, through this gray ice. And so as a result, during this ice cover period, you have a lake that is starved of light. Next. So, by the way, that was in a high snow year. Maybe just go back really quick.
Right.
Yeah, that was in a high snow year. Now, in a low snow year, you have a situation where you have, in the fall, just regular water. Then you have thicker black ice because you don't have a lot of snow that's falling on top of it forming that gray ice. And also that black ice gets really, really cold. So you have much more black ice formation that gets thicker ice. If you actually have a layer of snow on top, that actually acts as insulation. So it really does form as thick a layer of black ice. And so, of course, you don't have much snow in a low snow year, so you have very little gray ice and snow on top, and that proceeds through. So next slide. Then, that exact same scenario in a light situation, light penetrates, and light is able to penetrate through this thin layer of snow and gray ice and goes right through the black ice. And so in this situation, low snow year, you have light that actually goes into the lake. And that light is very important because it actually does a couple of things. It stimulates primary productivity or plant growth, which things feed on. And it also warms the lake up and causes circulation patterns to occur there. Okay. And so this is a picture not from one of our lakes, but this is an under ice picture from Lake Baikal, which tends to have these time periods where it has rather thick black ice. And you can see that there's algal growth actually growing on that substrate underneath. So photosynthesis going on. And one of the things about photosynthesis is it produces oxygen. So in lakes with really thick ice that's starved of light, everything that's living in there eats up all the oxygen, and you tend to have rather low oxygen water. Whereas in lakes where there's a lot of primary productivity, you actually have a fair amount of oxygen. Okay, I think I'm going to pass this off to Bill now, who's going to talk about some of our ice duration patterns.
Thanks, Steve. Bill Baccus, I'm an ecologist and physical scientist here at Olympic. So Steve did a great job of kind of letting you know what we do, and kind of what our studies and then how these lake systems work. And so now we're going to talk a little bit about what we found with our 20 years of studying these 8 lakes. So the question is kind of what do we know about snowpack trends, ice duration, and its influence on our mountain lakes? And so for starters, we know a lot about what our Olympic snowpack is. We've measured it here for 75 years, so we have a good feeling for how much snow we get. And through our work, we've come to know a great deal about the ice duration at our lakes. And the way we do that, Steve mentioned, sorry, I'm getting used to the microphone. Is this too loud? No. Okay. So Steve mentioned that we have these continuous instruments on an array. And that gives us a lot of information about temperature at the different levels within the lake. And so we developed algorithms where we can use this to determine exactly when the ice on occurs and when the ice off occurs. And you can just see a graph here. This is Fairy Lake in 2019. And it shows the surface temperature in blue and the bottom temperature in orange. And you can kind of see where they're the same temperature in the cool fall. And then as it gets colder, that surface temperature kind of drops near zero and the lake freezes. So we come up with our dates based on that information. And in order to make sure that, because we can't actually see what's going on, we put up time-lapse cameras at all of our lakes for a period of time, and then we're able to, a picture's worth 1,000 words, right? So we actually have photos of what's going on the surface of the lake, of our different lakes, and we ended up with 117 annual time series of these lakes, and we're able to compare them to what we saw in our data, and we found pretty nice correlation. Our ice determination method was within 2 days. It tended to be about 2 days, 2 days late, and our ice out was within half a day. So pretty accurate numbers. So we have a good idea about when these lakes freeze and thaw. And we published a paper in 2022 in Limnology and Oceanography, and found a few interesting things that we're going to talk about. This just shows a correlation. It's pretty obvious to most of you that the snow water equivalent, that's that snowpack number we talked about, And as your snowpack is deeper, this is your spring snowpack in May, as your snowpack's deeper, you have fewer ice-free days. So there's a very clear correlation. This just shows that correlation between snowpack and ice duration. And this is a little bit of a busy slide, but what it does is it looks at, Steve talked about all those different parameters that we've studied and collected data on. And what this is showing, and those are the different parameters on the left. And what this is showing is it's showing how we have in green, these are low snow years, and in purple, these are high snow years. And so with something like water temperature over here, you see how you end up with most of your green on one side of the scale and purple dots all on the other side. So where there's a split, then those are going to be parameters that are very clearly affected by snowpack. If your dots are kind of mixed up, then those are, it's not a strong correlation with snowpack affecting those parameters. Yeah, and so if anyone wants to look at that in more detail, we'll be glad to bring it up later, but not going to go into the details on that.
Can I just point out one thing, Bill?
Yeah, I'm talking the microphone.
I just want to point out one thing, and the one thing I just want to point out on this is, while this is really busy, is just like for water temperature here, you can see that in the low snow years, we have higher water temperatures than in the other. So there are these big differences between low snow years, say for temperature, and also say for in low snow years, you have more chlorophyll, you have more primary productivity because you have less ice. So there are real differences in those parameters.
Yeah, exactly. And another one, is that's really obvious here is this is zooplankton, which of course are feeding on that primary productivity. And you can see those are very separated as well. And here's like an easier way of kind of looking at what we were just talking about, say with surface water temperature. And so on your left here, you can see we've got this is the snowpack from 2010 to 2015. And you can see that very tall one on the left, that's 2011, which was a really deep snow year and a really late snow year. And then that kind of corresponds with some of the coolest temperatures we recorded. In this case, it's Lake Lacrosse. And then in kind of the counter of that, we had this unusual year, 2015, with a very small snowpack. And that correlates with some of the highest temperatures we've recorded. So another way of looking at it that's just a little more obvious. And so in terms of trends then, what we're able to do is go back and look at our lakes. And on the left here, this is the ice in day. So this shows the date. So between 1 and 365 would be the date. And so this is showing the day in each given year, the average day that we saw our lakes ice in. So this would be the day that each of the lakes froze. And so over the 20 years of our study, what we've seen is the numbers are really scattered and there's really no significant trend. The line shows a slight up, but it's not significant. And so we don't have a trend in the day that the ice in occurs. And just as kind of as a novelty, November 5th is the average day, but it's a really short range. So we see the earliest of all those years has been like October 26th, and the latest is like November 12th. So it's a very narrow range of time when it freezes. And that's because it really has to do with kind of the thermal mass, how warm that water is during the summer, and then how cold it gets. And typically around here, I mean, we're all familiar with it, we usually get that cold snap in late October, and it hits pretty fast and things freeze. So not a real trend. Now, in the opposite, with ice out, we did definitely see a trend. And so same period of time, again, you have your day of year over here. And you can see that it is still very spread out, but we do have a significant downward trend of about, so we're in the last 20 years, we're decreasing or we're melting out earlier by about 2 days every year during the 20 years that we've studied that. And the average ice out day for our lakes is July 9th, but you can see that the range is pretty incredible. We've had our earliest day of melt out has been March 6th in that low snow year of 2015. Our latest has been September 26th in 2011. So, you know, with ice on, we had 15-day range, and here you can see it's really spread out, 137 days. And that's, of course, because our snowpack is incredibly variable, whereas fall temperatures are pretty tight in terms of it's always cold and it's about the same temperature as it freezes. And so, yeah, so we're seeing that downward trend. And then, as would be logical, because we have that trend in the day that the ice out occurs, we also see a significant downward trend in ice duration. And that's being influenced again by snowpack and the date that the lakes thaw. And so just thought we'd kind of close this out with some conclusions and a little glimpse of the future. So we've kind of learned about how these lakes function and what we've seen and some trends in what we've discovered in our lakes. And some of you have seen my glacier talk. Some of these slides are kind of from that same thing. What we already know is that on this left, we have a slide, and those large circles show the larger the red circle, the larger the decrease in snowpack. And so in many areas in the Western United States, as I said, we've been measuring snowpack for about 75 years. And during that period of time, we've seen decreases anywhere from about 30% to 60% of the snowpack. So we know that there's a marked decline in snowpack. The Olympics, it's really quite obvious. This is one of our long-term snow courses up at Hurricane Ridge, and you can see a very obvious downward trend in the 75-year record there. So we know that our snowpack's decreasing, and we've seen how snowpack really influences the ice duration on these lakes. And so I always like, we're really fortunate in that in the last 20 years, when we had this long-term monitoring program, we were able to experience one of our coldest and wettest years. 2011 was kind of a record breaker in terms of a really cool spring and summer, a nice big snow load. So it was one of the biggest snowpack years we've had. And then in 2015, we had this very unusual kind of record-breaking low snow year. So in a short period of a study, we really managed to kind of capstone on both ends kind of what our range of environmental and climatic experiences our lakes could have. And so in 2015, it was really kind of a spectacularly warm year. And you can see on the left, it was a warm year, and there was very little snow. So you can see in 2015, that's the webcam at Hurricane Ridge, and you can see the high snow line is at about 6,000 feet in the Bailey Range there, and there's no snow kind of on the slopes in the Elwha Valley and in the meadows of Hurricane Ridge. And then down below is 1 year before on that same date, kind of what you imagine we would experience at Hurricane Ridge. And so this is just to show you how odd 2015 was. And then this just shows you the snowpack. And this is what your normal snowpack would be in terms of snow water equivalent, which is the amount of snow, and if you melted it, how much water would be in it. And this is what we had in 2015. So a very unusually low snow year. And what we know about, this is one of our lakes. This is Heather Lake in 2016. And this is what the lake looks like in a mean, in a year. This is winter of 2016. And our mean air temperature was about 1 degree warmer than normal. But it's got a nice, robust snowpack. And in the winter in 2015, even though we had a slightly above normal precipitation, it was about 4.5 degrees Fahrenheit warmer. And this is what that same lake looked like. You can see there's no snow on the slopes. It's barely frozen. This is kind of that black ice and a little bit of that gray ice that Steve was talking about, and we have a very thin cap of snow. So kind of thinking about what's going on in that lake this year. And over here on the left, I just want to point out, these are future climate forecasts. And so if you look at that green line, it goes across to kind of the projections that all the models say about our future air temperatures in the Pacific Northwest. And you'll see that that 4.5 degrees comes out to be about an average year in 2040 or 2050. So not too long from now. What we're seeing here is probably going to be closer to what our normal is. And so what did we see that year? So at the Olympic Lakes, which are over here on the left, this graph shows the number of additional ice-free days that we had at our lakes. So you can see that we had, on average, 79 extra days free of ice in 2015. The impacts were not quite as obvious at Mora, but at Mount Rainier, but that's still 50 extra days. And North Cascades was 40 extra days. And a lot of this is because the Olympics, as we know, the Olympic mountains are just a little more sensitive to warming. And because we have a marine environment and our mountains really at 5,000 feet, our average temperatures right now are about 29 degrees in the winter. So it only takes a little bit of a warming to really have a profound effect. Mount Rainier is a little bit further south, and their lakes are at slightly lower elevations. And so in a warmer year, you just don't quite see the same impacts. And North Cascades is still pretty close to Canada, and they get a lot more continental air masses. So it stays a little bit cooler. They weren't quite as impacted during the 2015 year. But, all of those are still pretty profound. And this is also just an interesting way of looking at it. So you can see the period of record of our 20 years. When we average those out, you can see the yellow is the proportion of the year that the lakes are thawed, which is about 35% to 65% ice covered. And in 2015, with that 4.5 degree warming, we saw a 23% increase in the direction. And it really flip-flops. Like all of a sudden, your lake is thawed 58% of the year versus only frozen 42. So going back to kind of everything Steve talked about in terms of processes, you can just kind of extrapolate and imagine, how this would be, especially if you have multiple years like this, and what that might mean, kind of looking back at that big scatter chart of the different parameters. And so kind of in conclusion, ice duration is decreasing in our Olympic mountain lakes. We've got earlier ice out, which is largely being driven by that decreasing winter snowpack. And then we found that we have relatively stable ice-on dates, which are driven by fall air and water temperatures. And one thing that we might speculate about that is, while we're not seeing that yet, some of that may shift as we have kind of warmer lakes. If we take multiple years with warmer temperatures in the summer, building up that thermal mass, then we might expect, over longer time, as that becomes more extreme, that maybe we will see that creeping up, but we have not seen that yet. So we've got the duration of ice cover decreasing, and more snow, longer ice duration is gonna mean colder, clear, and more dilute and less productive lakes. But what we're seeing is less snow and shorter ice duration, which of course is warmer lakes, lower dissolved oxygen, higher in nutrients, and generally more productive. And just a quick shout out.
Yeah.
That was Steve, very good one. Yeah, anyways, just wanna, like, a little bit of a shout out to some of our colleagues that have helped us with these publications. And then, of course, we've had, I think we tallied it up, about 80 field crew over 80 over the last 20 years, a few of which are in this room. And so we kind of, Steve pointed out the hard work in getting in here and taking this data. So thank you very much, you guys, for all the hard work on that. And yeah, we're open for questions. This is a time lapse, just so you can kind of this is Lake La Crosse, one of our study lakes, and that's O'Neill Pass and Mount Steele in the background. So you can enjoy that and ask us some questions.
Thank you. We do have time for a couple questions. We are going to be done at 8. I'm sure that the questions on this could go on forever, but we want to be respectful of your time.
On forever.
I know, we need to get home. So if you have a question, I see some hands already. Audrey will bring you the microphone, and we'll get through as many as we can. If you're online, go ahead and put your question in the chat. And when I can break in, I will ask your question for our presenters. Thank you.
Yeah, all of that.
So a couple questions. One was, and you said, I think there's only 3 lakes that were fish free in Olympic, and as far as the productivity and amphibians and like, were there even amphibians in the fishy lakes? And then increased productivity, what does that mean for our native amphibians in those high lakes?
Yeah, no, great question. And I thought for hours on this, but just to be succinct, fish have profound impacts on almost all the functions, from nutrients on up to sort of like amphibians, like you're talking about. Now, there are some amphibians, particularly when we talk about salamanders, that do reasonably well with fish, and some that don't do well with fish. So we have like northwestern salamanders, and we have long-coat salamanders, and one of those does reasonably well, coexists pretty well with fish, the other not. And so there is sort of a change in that community structure when you have the presence of fish.
And Janice, it's northwest salamanders are the ones you tend to see in the lakes. And one cool thing that I love about, and I've noticed this kind of floating around in some of our lakes that don't have, Lake Connie is one of them that has no fish, but it has northwest salamanders. And one of the really amazing things there is they're huge and they're neotenic. So they don't, they're these big adult bodied, amphibians with these gills that have it's almost like they've just decided there's no need to leave, right? And you'll be out there and you'll see like bugs on the surface and something jumps to get them and you're thinking, oh my God, there are fish here, and then you're floating around in the boat out there and you realize they're just these huge amphibians just cruising around like fish. So it's kind of an interesting thing.
Sort of like teenagers that refuse to go home.
Yeah, exactly.
So, Bob Freeland, and since both of you are neighbors, I wanted to let you know that you've got a place to stay when Doge finds out you're doing it. And you use that unmentionable phrase, climate change. Good news is that apparently you can still say climate crisis and climate disaster, which may become more common now.
Was there a question there, Bob?
The question is related to a lake that apparently you're not studying, and that's Lake Angeles, which does have brook trout in it and a non-native fish. The good news there is that there's no license required and no limit. The bad news is that I've been told you can't eat very many of them because of the amount of lead in the fish.
Not lead, and you can eat as many as you want, but, it's mercury, it's mercury.
Mercury.
Yeah.
Mercury, that's
Yeah.
right.
Yeah.
Mercury there. And then today I read in Science that you can't drink rainwater now because it's got microplastics in it. So I'm wondering.
Wow, now I'm
Sorry
impressed,
about
wow.
that.
Yeah, I mean, yeah, our fish in our high mountain lakes do have really elevated mercury levels. Talked about that for quite a while also, but I guess the point is that there are some advisories in terms of how much you should eat, particularly if, let's say, I don't think you are in this category, but if like you're a pregnant female, you probably shouldn't eat a whole lot of those fish. But those are rather conservative estimates. And the number of meals that people are getting when they visit our high country and eating trout from these lakes, it's not really that much of an issue. If that was like 30% of your diet on an annual basis, then you should probably be eating something else.
Yeah, it's mostly like guys like Tom Schindler that would probably sit by the lake and just eat fish all day long while he was a backcountry ranger. That's where you start getting the guilty.
I'm just wondering, if you think of humans, mammals as agents of nutrient delivery, they need space to distribute all of this through these lakes. You see, like, there are big difference in the that productivity in the lakes that have a lot of human visitors versus the lakes that don't have a lot of human visitors.
Yeah, so the question was, when in lakes that have high visitation, do we see higher productivity levels? And the answer really is, well, two parts. One, we don't have a huge sample size for that comparison. So I'm going to wave both hands here. But I will say that in reality, no, not really, because the level of visitation, even though for those of us who have lived in this area for a long period of time, we've seen visitation go up, it's still not that big. And also the park actually, has in those high visitation areas, we actually have privies which are used fairly well that contain a lot of particularly that human waste. So, I mean, there are other types of contaminants that, are potentially a worry, such as PFASs and things like that, and that people leave in the environment. Plus, as Bob mentioned, plastics, which are not coming from visitors, which are actually atmospherically deposited all over the globe. So, yeah, there are a bunch, but from a nutrient perspective, at current visitation levels, it really is not a big issue that we have right now.
Two questions from online about fish. People apparently really care about them. How will the diminished snowpack and increased algal production affect the trout populations, swimming, and fishing conditions? And then also, not related to ice so much, but do you know why there were so many fish carcasses floating on edges of sun-up lake shores in September last year? Was the lake warming?
Can't possibly tell you about Lake Sunup, although if there were a bunch of fish carcasses that were in the early summer or the spring, that it may very well have been due to a phenomenon called winter kill. So a lot of times in lakes that have rather thick snow and ice, as I mentioned, light's not coming in, and particularly if you have fish in there, these fish are running around under the ice, breathing a whole bunch, consuming oxygen, driving oxygen levels down. And this is a phenomenon that you see a fair amount, that they basically asphyxiate themselves because they burn up all the oxygen. So that could be what's happening there. I don't know in that particular example, so I don't really work in that lake. The other question was about fish, and as these lakes have less ice cover and more productivity, what does that mean for fish? Well, it's probably actually pretty good for fish, because as you have more productivity, you've got more fuel being pushed through the food chain, and as a result, you got more fish food. And if you've ever looked at these lakes and been up there and caught these fish, they appear like little snakes because they don't have a whole lot of food. Okay, but I would say it's probably good for the fish, but these fish don't belong up there anyway, because it's the non-native species up there. And one of the things I would just sort of point out also, that when we had that big complicated slide of the high snow year and the low snow year and the difference in all those parameters, almost all of those parameters were measured during the summertime. And I think this was one thing that we didn't really hammer home, that I want to hammer home to you, that changes in ice duration not only affect what's going on during the winter, but they have effects that propagate over to the summertime. Okay, so what happens during the winter affects what you see during the summertime. And I think that's a big take-home message here. All right.
I think Tom had a question. There were years in Royal Lake that I saw growth on the bottom of the lake that in August or so would float up to the top and make these mats.
Yeah.
And I don't remember whether it was more or less on, I didn't pay attention to how much ice there was the winter before. Right. When I saw those. Is that something we're more likely to see as things warm up?
Absolutely. So the question was seeing these benthic algal mats that grow on the bottom that then start breaking loose and going all over the place. And yes, that is actually something that we're seeing worldwide in mountain lake systems with climate change, that you're seeing more nutrients in the lakes, more light level, and that is so as I showed you that photo of the algae growing on the underside of ice, algae are very opportunistic. They need, by and large, a lot of substrate to grow on. And since a lot of these lakes are relatively shallow and the light penetrates all the way to the bottom, and there are a lot of nutrients in the bottom also, you'll get algal growth on the bottom, particularly with warmer water temperature. And then you see these unsightly algal mats that then break apart and float all around and are not the normal state. So that sort of greening of mountain lakes is something that we're beginning to see in our network. We're actually seeing more of it right now. We've got a couple of these 20 lakes over in the North Cascades National Park. They've really noticed it in a couple of their lakes. And we haven't quite seen it in our study lakes, but we expect with time that we're going to be seeing more and more of that. And that actually, from a visitor use, from an enjoyment perspective, is something that we're going to probably be seeing as these lakes change, as warming occurs. It's going to change the character of these lakes and how people experience them.
Another question?
I just wondered if the park ever considered getting rid of the trash since they're not native.
Well,
They're doing
that's
that.
above my pay grade, sister, but I will say, I will say that there are other parks in our network that have. So North Cascades National Park is actively removing fish from their mountain lake systems. I believe Mount Rainier is experimenting with doing that. And it's not something that Olympic is doing yet, but watch this space. It'll be one of these things that I think from a park management perspective is something will have to be considered into the future.
Oh, I was just going to say another kind of side piece of the importance of not having the fish in these lakes is that as our snowpack in these subalpine basins becomes less and less, a lot of these small snowmelt ponds that are is kind of the refugia for these amphibians now, because the lakes are a bit of, even with the Northwest salamanders, the lakes are more of a hostile environment for like young amphibians. But what we're seeing in years like 2015, these snowmelt ponds don't have any water, or there's not snowmelt water in there long enough for a full life cycle of these amphibians. So the lakes are going to become more and more important for our amphibians. And so in the future, since amphibians are kind of one of those species that are getting it from a lot of sides with environmental change, that may be one of our reasons to kind of look at that, because we may need these lakes as refuges for these species. Yeah.
Over the next 20 years of your ongoing research, do you expect to add eDNA, and would that be an important component?
We've actually already started using eDNA. We've been doing it for about 8 years now. And so we're in the middle of a publication with Sam Brinkman where we visited 117 of the 180 lakes that we could potentially get to. And so we've already started that. And at our mountain lakes, we've developed a protocol where we are now both, looking for amphibians with visual surveys and also taking eDNA. So we've done that maybe a decade now almost.
Yeah.
Yeah. So yes, we absolutely are.
What's eDNA?
Oh, thank you.
eDNA, great question, is environmental DNA. So organisms that are in the environment, like particularly fish and amphibians, are constantly shedding material, slime, think fish slime. And so you can go through the wonders of modern molecular biology, you can go and grab a water sample and put it onto a very, very fine filter, and then take it back to the laboratory and analyze it, the DNA that's caught on that, and you can identify species. And so, as Bill mentioned, we've gone as a collaborative project from our shop along with our fisheries shop. We've looked at 117 of our lakes, and we're looking specifically to the goal of that project was specifically to look at the history of stocking, because actually a lot of our lakes were purposefully stocked in the 40s, 50s, 60s, and even into the early 70s. We're stocked with non-native fish. And so we are looking at those stocking records. We've gone back to all the lakes that we can get to that actually we know were stocked, and a bunch that weren't also. And we're looking at both the fish communities there and the amphibian communities. And that is data that we're still currently working up. But I can tell you, because it's almost done, is that we do see differences between, surprise, surprise, where you actually have fish and what those amphibian communities are. And we actually have another study that we've done, which is a corollary study to that, which actually looked at lake districts, a bunch of lakes, and then wetlands and these vernal or temporary ephemeral ponds nearby to actually get at this bit that Bill was talking about how amphibians are using the non-lake wetland, wet landscape. And as climate change happens and those areas begin to dry up and they need refuge habitats, and basically what impacts potentially fish have on that. So that's a lot to answer that question.
Last one.
All right.
Last one.
Hello, I'm very interested in wildlife ecology. You mentioned that some of these lakes are petri dishes and that you study everything from, amphibians to the microorganisms. So I'm curious if you have ever studied like species distribution or biodiversity in these lakes from the approach of island biogeography. If it's even accurate to describe any of these lakes as biological islands, or if they're generally like more interconnected than that.
Yeah, it's wholly accurate to be able to describe these as islands. But have we looked at it from an island biogeographic perspective? No, not really, because as with most things with science, it depends upon what your question is. And our specific question or set of questions here was less having to do with connectivity between these and from a biodiversity perspective, connectivity, and more having to do with what is the status and trends in these lakes over time. So it's a sort of a different set of questions, but these lakes would be wonderful for asking those sorts of questions. And we, within each one of our lakes, we do have wonderful biodiversity data. So for instance, we take zooplankton, which are these really rich communities of animals that live up in the water column. And we're actually working on a paper right now looking at and characterizing that in these differences and trends. So there you go.
Okay, thank you. We are going to wrap up for the night, but we appreciate our speakers. Thank you.